All right. So a couple of things off the top. So I think there's a little bit of confusion on an Excel assignment. When I'm talking about population parameters, the only reason I'm using that language is you're dealing with sample data. But remember, when we build a confidence interval, we do hypothesis testing, it's about where that true population mean or proportion lies. All right, so you're treating it just like we did all the Excel stuff that we did in class with the rental price data and then the UFO sighting data. You kind of got your sample and you're building these confidence intervals, and then the last one is hypothesis testing for where that true population parameter is. So what we did last class was we talked about these things called p-values. So just to kind of give a quick review of what we were doing. So we'd start out, actually, I'll just work off this example. So we'll start out with some null and alternative hypothesis, right? So the alternative hypothesis we said is what we want to test for, right? I won't use this terminology, but you'll kind of see the null hypothesis is what we want to test against, right? So whatever we're trying to test for, that's what we identify first, our alternative hypothesis. So here, a researcher, expects that average back to school spending differs from this amount that this group put out. So if we're thinking about, does this true population mean differ from that value, what should we be thinking about? What sign in that alternative hypothesis? Being different than is the same as not equal to, right? Being different from a value means you're not equal to that value, right? So once I know the alternative, what does the null have to be? Well, I assume the opposite is true. I stack the deck against myself, or I assume that it's exactly equal to that value, right? So we know that the sample means if what I'm assuming to be true is in fact true, then my sample means should be centered around that value, right? So if what I assume to be true is in fact true, my sample mean will be centered around that value. So for this one, I think we're just asked to identify the null alternative. So we should be, where is that? A, right? So notice here, C, you've got another option where you've got kind of, did I say A? I meant B. I was looking at this wrong. So you'll notice on C, you've got a similar option that has a not equal to sign in the null alternative hypothesis, but it's using that value of 622, which was your sample mean. So the value that you're thinking about in your null alternative hypothesis, that's not coming from your sample data. That's coming from something that you're wanting to try to test for, right? So in this case, I want to test to see whether or not this trade group is wrong, right? Or maybe, another example, I'm testing to see whether or not the average weight of my product is different from a certain amount, right? So what I'm going to do is then assume what I'm trying to test for against is the true value. And then I'm going to use my sample data or my sample mean here to see if, based off of what I saw from that sample mean, is it inconsistent enough with what I assume to be true that I can reject that assumption, right? Or I can reject the null hypothesis. Well, how unlikely is too unlikely, right? Well, we said we can think about, we've got different tests. I think we did a left-tailed test last class. We've got right-tailed tests, and we have two-tailed tests. So this one would be what type of tailed test? My alternative hypothesis would be right-tailed, right? So think about this way. The type of tailed test is saying what values could go against the null. What values on what side could go against this null hypothesis? Values on either side. Yeah. So I've got a two-tailed test. Okay. So usually what I would do to find that, what we were calling a p-value, right, which just represented the probability that I saw the sample mean that was as inconsistent with what I assume to be true is what I saw, or anything even more consistent, right? Or anything even further away from that assumption or that assumed true value. So for this guy, we're kind of looking for the area in the right tail. Right? Now, the problem is when we have a two-tailed test, we only see one sample mean. But if I'm thinking about what's the probability I saw sample evidence that was as inconsistent as I did, Well, now if I had seen something that was as inconsistent, but on the other side, well, now values over here would also go against my assumption. With a one-tailed test, they wouldn't have. They would have just supported the null. But with a two-tailed test, for every value in this range on the right-hand side here, it would have been equally as likely if I could have taken, I only have one sample. If I could take more sample means, it would have been equally as likely that I would have seen a value that was that far away from that assumed true value, but on the other side. So we can find the area in this right tail, but when we're looking for that p-value, we said we would then have to add one more step, which is multiply by 2. Right? I've got two tails of the same size or two probabilities that are exactly the same. Okay? So if I'm thinking about what the p-value of this hypothesis test is, how am I going to find them? Well, I need to turn that sample mean into what we were calling, well, it's just a z-value, but we gave it a more specific name, which is a z-statistic, right? Because the z-value represented, so if we were turning sample means into z-values, usually we subtracted the mean divided by that standard deviation of our sample means, which was the square root of the variance over the sample size. Okay? But that's a z-value. If we want a z-statistic, it's just kind of semantics, just kind of what we're calling it. But the reason why we don't just say z-value, we say z-statistic, is because it's the number of standard deviations away that our sample mean was from the assumed true value. And right, we can do multiple hypothesis tests so that z-statistic is always not relative to the true mean, but relative to whatever we've assumed that mean to be. So I go ahead, I got everything that I need. All right, I plug my values in here. So the sample mean is 622. Assumed true mean is coming from my null alternative hypothesis, 606. I don't know. I think I had the variance, what, 4,225, and then a sample size of 30. Calculating these z-statistics, it's just a matter of plugging those values into that equation. Okay. Now, if I'm looking at this, right, which of these, or can I rule any of these out? Well, I saw sample evidence on the right-hand side, what I assume to be true. So my z-statistic should be a certain number of standard deviations above, so it should be positive. Can't really rule any of these out. C and D look pretty low. I mean, I really can't say unless I calculate what the actual standard deviation is. But my guess is, those look a little bit low, right? I mean, the standard deviation, or the z-value is some of the number of standard deviations away, probably not 0.08 or 0.16. But, so we can't really rule out a whole lot, but we're going to go to just kind of that equation, plug everything in. Well, maybe we'll check my math there. Maybe I didn't do this right. Well, it doesn't overly matter, but for the sake of making sure that we're doing this right. So 622 minus 606 divided by the square root of 425 divided by 30. Okay, so it is about right. I rounded, so I'll go back and change those slide with the options. I'm not sure why that wasn't there. But regardless, right, we have to go through these steps, plugging in those values, kind of figure out what that z-value is. Okay. So I found that this was 1.39. Okay. So 1.39 standard deviations away from what I assume to be true. I can use my z-table now to find that area in the right tail, but I have to remember I've got a two-tailed test. So I then have to do this added step of then multiplying it by 2. So I go to that standard normal table. And there we go. So I go down to what? Second decimal is 9. So we'll use that last one. 1.39 is 0.9177. Right? What did I do wrong here? What does the table always give me? That standard normal table. Always tells me the area to the left. So if I wanted the area to the right, I have to subtract that from 1. Okay. So this is where drawing the visual out and thinking about what you're looking at. I mean, automatically, like the area in this tail has to be less than what? 0.5. Right. So right away, that would help me. Okay, I'm not thinking about this right. I've got this. Oh, yeah, I've got to subtract this. Table gives me the area to the left. I want the area to the right, so I can subtract it from 1. So that's what? 0.0823. I'm looking at this right. Then to find my total p-value for this two-tailed test, I would then multiply it by 2. Okay. So what's the final step? I now have this p-value, which represents the probability that I saw the sample mean that I did that was as inconsistent with what I assumed to be true, or anything even more inconsistent. Yeah.
Compare it to the alpha.
Yep. So remember, we were setting these threshold alphas, which were essentially saying, okay, if the probability of seeing what I did from my sample, if what I assume to be true is in fact true, if that probability goes below a certain threshold, then I'm okay rejecting what I assume to be true, because it probably isn't, right? That probability is so small that it's probably way more likely that my distribution is centered around a higher or lower value, depending on the example. So we have these different alphas. Really, for any test, we can make rejection decisions very quickly at every single level. So what we'll kind of call these, I don't think I quite got there last class to represent this. So we're going to start thinking about, so here's my alphas of 0.1. There we go. 0.1, I'll move out of the way in a second. 0.05 and 0.01. We're going to start calling these kind of significance levels of 10%, 5%, and 1%. You can kind of think about those would correspond to what confidence levels? 90, 95, and 99. All right. So we typically, just the way that things are reported with hypothesis tests, you don't say, I don't know, it's just, I don't know, just the way that kind of people, there's somewhat of a reason why people like to say things at different levels of significance as opposed to confidence. Confidence, reporting it in terms of a percent of confidence is usually left for confidence intervals. Hypothesis testing, we usually say we can reject it at these significance levels. Once we get to linear regression, we'll kind of see why that's the kind of convention. But for now, just know that all the significance level is the area that would be like outside of your confidence level. All right, so 90% confidence, 10% significance level, that's the alpha of 0.1. Right? So here, if my p-value is what? 0.1646, is that less than 0.1? Not a trick question. No, right? 0.16 is not less than 0.1. So I would say that I failed to reject, right? And then if it's not less than 0.1, it's definitely not going to be less than these others. So here, I'd have a situation where I failed to reject the null at any reasonable level of confidence. Okay? But what if I wanted to be able to reject this at the 80% confidence level? What would my alpha be there? So 80% confidence would be what level of significance? 20. And then alpha would be 0.2. Yep. Is my p-value less than that alpha of 0.2? Yes. So at the 80% level, I maybe could reject, right? Now, it depends on what level of confidence or what significance level I want to be able to reject this at, but we can test against all of them, right? And in fact, another way to think about this p-value or interpret it is your p-value represents the very first alpha value, which you will no longer be able to reject the null, right? Think about it this way. 0.2, I could reject. 0.19, I could reject. 0.18, I could reject. 0.17. Once I get to 0.164, the p-value is no longer less than that, right? It's not less than or equal, it's strictly less than. So the p-value kind of represents like that last threshold alpha for which you can represents the threshold alpha for where you no longer can reject the null at, right? You start failing to reject the null at that level, okay? Any questions here before we keep moving? Okay. So I've got another example for sample means with known population variances. I might save that if we kind of go through more on Friday. I'll kind of throw in that example so we get a little bit of taste of all of them. But I want to introduce the idea of how we would do this for sample proportions today, as well as introducing the idea of critical values. Now, critical values are going to be very closely related to what we're doing with p-values. It's just a slightly different way of thinking about this. Okay. So if we wanted to do these hypothesis tests for proportions, it really is just going to be a matter of the difference in notation, right? The proportion is a unique case of the sample mean. So we've still got left, right, and two-tailed tests. They got out of the way here, right? It's just now we have some assumed true population proportion, and we're using our sample proportion as the best guess of where that population parameter is, right? We're trying to rule out these different assumed true values. Everything's still the same. I look at my alternative hypothesis. The sign of the alternative hypothesis tells me what type of test it is. If there's a greater than sign, it's a greater than test. Less than sign, less than test. Not equal to sign, two-tailed test. Okay. So nothing's changed really, other than that we're just looking at a proportion now. So here's kind of our steps. Everything's going to be exactly the same, but before I do this, everything's going to start out exactly the same. We'll determine the null alternative. We'll figure out what level of alpha we want to test against. You can use the p-value approach with proportion examples. I'm just going to introduce with some proportion examples how we use the critical value approach. So we could use the critical value approach for sample means when we knew the population variance. We can use it for proportions. We can use either one in either scenario. So just because I'm introducing it to you here doesn't mean you always have to use the critical value approach with proportions, right? And I'll try to kind of show you both as we work through the first example. So what we're going to do with this critical value approach is think about, I've got my sample proportion distribution, and I'll show it to you for a left-tailed test first. Okay. I've got some assumed true value. Okay. What I'm going to think about is I can, if I'm setting this threshold alpha, I'm essentially saying, well, that's the kind of highest area in the tail that I'm okay with. Okay. So usually what we did was we then took our sample mean and then turned it into a z-value, found that p-value, and compared it to alpha. Okay. But if I wanted 0.05 in this lower left tail, I also know that there's a specific z-value that would give me that area. That specific z-value we're going to call our critical value. Okay? You can almost think about the critical value is the z-value that would give you whatever your desired alpha is in that tail. Sounds like something's about to explode over here. So we would just be kind of using that inverse process. We know the area we want in the tail. We can figure out what z-value would give that to us. That's all our critical value is telling us. Then, instead of comparing alpha to a p-value, we'll have this critical value. And what we would know would have to be true is that if we saw any sample mean in this range, if we turned it into a z statistic, it would have to be larger in absolute value. We're dealing with all negative values here, so I'm not going to say less than or greater than, but like larger in magnitude, right? So if I'm setting this threshold alpha, I know there's a corresponding z or critical value that would go with that. Then if I see any sample mean that when I turn it in, in this range, when I turn it into a test statistic, that test statistic will be greater than my critical value. Or think about it this way, I'm setting with my critical value the threshold number of standard deviations away I'm okay with before I start rejecting the null. If my sample evidence goes any more standard deviations away from what I assume to be true, then I'm going to reject the null because it probably isn't true. So what we're doing with the critical value approach, no matter if it's a left, a right, or a two-tailed test, if we think about it, whenever that absolute value of the test statistic is larger than the absolute value of our critical value, right? Or all I'm saying there is that z or that test statistic is greater than my critical value in magnitude, like larger in magnitude, then I'm going to reject. So just like alpha was like this threshold probability that if the probability gets any smaller than this, I want to reject. The critical value is saying, well, this is the threshold number of standard deviations away I'm okay with. If I go any further than that, I got to start rejecting, right? So what's going to be true for our three kind of conventional alphas, 0.1, 0.05, and 0.01? What's going to be true about all three of those critical values, right? So every time I would have a different level of confidence, it has its own critical value, right? Because alpha is changing there. So what's going to be true about the critical values for a left-tailed test?
Negative.
Yeah, they're all going to be negative, right? They're on the left side of that standard normal distribution. What if I had a right-tailed test? It's going to be the exact same values because I still have like the same three kind of benchmark alphas, but my critical values would be positive. So we kind of add this step in where we figure out where our critical value is. And then another thing, you can use this rule, right? The absolute value of your test statistic is greater than the absolute value of your critical value, then you reject. Or you can kind of create this nice visual where once you have that critical value, you just draw an arrow into the tail and think about it as that's my rejection region. If I plot my test statistic against my critical value, if it's anywhere in that rejection region or anywhere where I kind of drew that arrow into the tail, then I'm rejecting. Right? Same thing would be true if I had a right tail test, the arrow would just be going into the right tail. And then if I had, and we calculate our test statistic, we plot that test statistic and see if it's in that region. And I'll come back to this in a second. I want to show you a picture here real quick. Oh, that happened. There it is. So you can think about, for my left tail tests, I can find these Z values that give me alpha in the tail or my critical value. Rejection region will be the area to the left. For a right tail test, I find that critical value, they're positive. Rejection region will be the area to the right. For a two-tail test, it's a little bit tricky, right? Because I need to know the alpha that I'm setting is still that threshold probability, but I know that evidence on either side goes against the null now. So I need to have a total of alpha in my tails, because I now have two tails, right? So I need the Z value that gives me alpha over 2 in each tail. So I'm actually, for a two-tail test, going to have two critical values, right? So I would plot those. They're going to be the same value, just one's positive, one's negative. So two-tail tests look a lot like what? What we were doing for confidence intervals. All right, remember with confidence intervals, we're always going, how many standard deviations do I need to go to get alpha over 2 in the tail? Here, the number of standard deviations away I need to go to get alpha over 2 in the tail. So those would be kind of visually how we would think about our rejection regions. If we want to be a little more specific, here it is. You can like write this out differently for left, right, and two-tailed tests. It just gets tricky, you know, because with left-tailed tests, we're thinking about negative values, so I need my test statistic to actually be less than. To avoid all of that and any confusion, you want to use an equation, just take the absolute value, and that'll work for any type of tail test, okay? So if you take the absolute value of your test statistic and your critical value, you should be able to make the correct or rejection decision no matter what type of tail test you're looking at. Okay? So I wouldn't even worry about this slide. I'm just kind of using this more to show like, just complicates it if you try to treat it differently for a test. Just always take the absolute value of both and compare that. Okay? So you can kind of think about, you already mentioned this, but anytime we have a right tail or greater than test, our Z values or our critical values are positive. For left tail tests, they're going to be the same values but negative. And then the two tail test will have two critical values, and it won't be the Z values that give us alpha in one tail, but alpha over 2 now in each tail. Okay. So you'll notice if I look these values up for a right tail test, so I go 0.1 is that area I want in the upper right tail. So when I go to the table, I'd actually look up 0.9, right? I'll find 1.29. And then if I wanted 0.05 in that upper right tail, well, the area to the left is 0.95, I look it up, I'll find 1.65. These values are always going to be the same. Your critical values for a standard normal distribution are always going to be these values here. I mean, you can look them up, or you can, I guess you could memorize them, but I would suggest, we want to get used to this process of knowing the area that we want in that left tail based off of what type of tail test we had, and then looking at that value at the table to then find that critical value. But like I said, at some point, you're probably going to be getting familiar with these as we work through more examples. That set of practice problems I got up on Kano, so maybe want to start kind of working through the later problems if you want more hypothesis testing and stuff. So notice for the right tail test, I've got the same values as I do for the left tail test. It's just for that left tail test, my critical values are negative. Right tail test, they're positive. Yeah. Oh. And then here, I'm not looking up alpha for a two-tailed test, right? For a two-tailed test, I've got alpha total in my tails now because I've got multiple tails. And a marker that doesn't work. So when I'm thinking about, I want to find these z values, these critical values, I need to find the number of standard deviations away I need to go to get alpha over 2 in each tail. So it's just a matter of now for alpha 0.1, I would look up half of alpha, or 0.05. Well, notice, I already did that for a one-tailed test. It's just that that critical value of 1.65 is going to belong to a different alpha if it's a two-tailed test, right? Because alpha gets split up into two tails now. But it's the same process. Once I divide alpha over 2, I just go to the table. That's the area I want in my tail. And I can kind of figure out what my critical values are now for a two-tailed test. Questions on this? I'll show you one more way of thinking about this in just a second. But there's something before I forget that I skipped over. I want to go back and mention. So the other difference that we need to be concerned with is that when we had this test statistic equation for my sample mean, we said it looks something like this, right? Where what's in the denominator represented that standard deviation of my sample mean. If I want to turn a sample proportion value into a test statistic or a z statistic, well, oh, sorry. I'm no longer using my sample mean value, right? I'm now looking at my sample proportion. I'll no longer subtract the assumed true mean, but the assumed true proportion. And then I want to divide by that standard deviation of my sample proportions. The only problem is we said that technically should be p times 1 minus p divided by n. But we don't know the population proportion. Remember when we're doing confidence intervals for sample proportions? We said, well, what do? We'll use the best guess that we have, which is the sample proportion. But here, we no longer use the sample proportion because we're assuming the true population proportion is a certain value. So before, because we don't have the population proportion, down here, we're going to use that assumed true population proportion, right? That's the whole point of this test. We're assuming that this is the true value. So if this was the true value, this would give me the actual standard deviation of my sample proportions, okay? So a little bit different, but it's the same setup every time, right? Take your sample statistic. How far away is it from that assumed true value? And then by dividing by the standard deviation of that statistic, well, that converts how far away you were into the number of standard deviations away that you were. Right? So it's the same process. It just looks a little bit different for proportions, right? The formula looks a little bit different. But it's still telling you the same thing. It's how many standard deviations away your sample statistic was from that assumed true value. Okay. Questions up to this point? We'll work through a couple problems here. Well, we'll work through one, and then I got another way of showing you something about critical values and then p-values. So we've kind of already talked through this. Here's our steps. I kind of already mentioned, right? So we're going to start out the same way, right? 1, 2, and 3. We still calculate our z statistic. It's just now instead of using that z statistic to find a p-value, we'll use our alpha to find a critical value. And then the fifth step, we're no longer comparing the p-value to alpha. We're saying, does that test statistic fall somewhere in our rejection region? Or another way of saying that was, is that test statistic larger in absolute value than the critical value? Okay. So let's go to this first problem. Okay. I get a tricky one. So let's assume that you want to test for whether or not, well, I'll probably change this in a second, but let's say you want to test for whether or not, well, I can show you on my, whether or not more than 50% of people own a gun, right? So if we're trying to identify our null alternative hypothesis here, Remember, our alternative hypothesis is what we want to test for. Okay? So if I want to test for whether or not more than 50% of the population owns a gun, what would my alternative hypothesis be? Yeah.
That less than 50% of the population.
So we're thinking about that alternative and null hypothesis are complements, right? But whatever I'm trying to test for, right, that's what I'm going to be putting in my alternative hypothesis. So actually, wait, whether or not, oh yeah, so whether or not more than 50%, right, means that I'm trying to find, is that population proportion greater than 0.5, right, greater than 50%. Now, I think what you're thinking is, well, my null hypothesis, what I'm actually testing against and trying to reject, will be the exact opposite of that, which is that it's less than or equal to 50%. But it's always like what you're given in the problem, like that's what you're testing for. You kind of have to start out with your alternative, and then the opposite of that is your null. So I've got what type of tail test here? If I look at my alternative hypothesis, got a greater than sign or a right tail test. So I'm thinking about the distribution of my sample proportions. If what I assume to be true is in fact true, it'll be centered around that value of 0.5. So for a right tail test, you can kind of think about it as only evidence on the right side will go against that null. So we're going to work through this one because I'm going to prove to you that even if you could work through the entire thing, but this is actually a really easy one. So once I know this is a right tail test, if my sample proportion I found from 100 homes was 0.41, do I reject or fail to reject the null? Very quickly, you should know the answer. If I've assumed that that population proportion is less than or equal to 0.5, I found a sample proportion of 0.41. Does that go against my null? No, it actually supports the null. So why the hell would I reject it, right? This one, I already know. Well, I saw evidence on the left. I saw evidence on the left-hand side that actually supports my null. So I don't even have to go through steps if all I care about is my rejection decision here. I'm going to work through the steps that even if we had some evidence that went against it, I'll kind of show that if we work through this, the rejection process and the rejection decision will end up being that we fail to reject, right? But we already kind of know that ahead of time because we found evidence that supports it. So if instead I go through the entire process here and I think about, I've got a right tail test. First of all, which of these can I rule out if I've got a right tail test for my critical values for the 1, 5, and 10% level? Or 99, 95, 90% confidence. It's a right tail test. My critical values have to be on the right side of our standard normal distribution, so positive. So right away, I know B and D can't be the answer. When you're taking the test and I'm giving you these options, cross things out, right? You know for a right, like this is right tail, the right side of that distribution, you're only dealing with positive values on that standard normal distribution. So essentially what I'm trying to do is find that critical value that gives me these 3 desired areas in the tail. Once I find that critical value, my rejection regions will be the area in that right tail, right? So I'm going to go to my standard normal table and I can look these values up, right? So the only problem is if I look up 0.01, 0.05, and 0.1, 0.05, and 0.01. So notice if I look up 0.01, where is it at? Right in between these two. So negative 2.32 and negative 2.33. So negative 2.33. Well, notice if I just look up alpha here, if it's a right tail test, alpha, when I'm looking at this table, that's the area in the left tail, right? Technically, for a right tail test, if I want 0.1 in my upper right tail, what's the area to the left? I've got 0.1 in the upper right tail. What area has to be to the left? 0.9. So I really shouldn't be looking up 0.1 when I go to the table. I should be looking up 0.9. Now, the thing is, if it was me, I would just look up 0.1, and what could I do? We just found it was negative 2.33. So what is the critical value that would give me 0.1 in the upper right tail have to be? Actually, I wrote these backwards. I'm looking at I'm pointing at the wrong thing. We just looked up 0.01, sorry. So if I know that the area to the left of negative 2.33 is 0.01, and I want the area in the upper right tail to be 0.01, what would my critical value be? That same value, just positive, right? And I can prove that to myself. So here, for an alpha of 0.01, the area to the left would be 0.99. So I go down here, I find what's closest to 0.99. I'm in between these values. Sure enough, 2.3, in between 2.32 and 2.33. So you can just use alpha to look up your critical values. And then just remember, if I have a right tail test, it's those same values, but positive, right? So for instance, if I look up the other two, alpha of 0.05, it's in between these two. No, sorry, that's 0.005, isn't it? In between these two. So 1.64 and 1.65. I'll use the higher of the two. And then my last alpha of 0.1. Where can I get that? Looks like I'm closest right in between these two values. So 1.2, negative 1.28, negative 1.29. I got a right tail test, so it's going to be that value of negative 1.29, but positive. Okay. So now that I've got these critical values and I know my rejection regions, all I would do is turn that sample proportion into a test statistic. Now, this is very easy. It doesn't matter what the actual value is, because just from having plotted these points, I know that my test statistic or my Z statistic is going to be what? Less than 0, right? It's going to be a certain number of standard deviations below what I assume to be true. Well, that's going to be nowhere near the rejection regions. Now, we knew this ahead of time. We said, well, yeah, duh, we found evidence that supported the null. So of course we should fail to reject it, right? Of course, that test statistic isn't going to be anywhere near those rejection regions. Okay. Now, if I had found maybe, let's say I found something on the other side. So let's say I found like 0.59, right? Well, now I have to turn that into a test statistic, plot it against my critical values, and see which of these rejection regions is it in, right? The way that I drew this here, like let's say, I don't know, let's say that test statistic is 1 point, not 1 point. Yeah, actually, that'll work. 1 point, let's do 4. So I plot that where my test statistic is. It's in my rejection region for an alpha of 0.1, or at the 10% significance level. So I could reject at a 10% significance level, or 90% confidence. But it's not in the rejection region for my alphas of 0.05 or 0.01. So I would fail to reject the null at that 5 and 1% significance level, or at the 95 and 99% confidence level. Well, plot my critical values. I'll then turn my sample evidence into a test statistic and plot that test statistic against those critical values. If it's in my rejection region, I can reject. If not, I fail to reject. So now the actual one here, right, isn't very interesting. But if I had something that looked a little more, on the right-hand side, it might be a little bit more interesting, right? So I've got a couple other examples we'll look at. But we've already identified the critical values here. If we turn this into a test statistic, all this is going to be doing is looking at that test statistic formula, plugging in your values. All you have to do, you'll be given a sample proportion. You'll be told the sample size. Your assumed true proportion is going to come from that null alternative hypothesis, right? So for us, it's going to be 0.5, all right? Then it's just a matter of getting everything plugged in. Okay? You want to break it down in steps, find the standard deviation first, so that you only have one value to plug in there. You don't have to worry as much about parentheses. But really, this part's going to be too tough. The test statistic equation should be some easier questions on the exam, because you'll have those formulas in front of you. So it'll just be a matter of plugging in those values. Okay? And I use the same notation. So, when I'm looking at those practice exams, like if you see p hat, hopefully you can figure out that I should be using that test statistic formula instead of the one that has sample means, right? At the very least, just try to match up the notation to the formulas. And we'll look at that formula sheet a little bit on Friday and kind of break it down a little bit. I want to see ways to remember some different things. But for now, the very worst you can do that, right? Just kind of match up the notation. All right, so we didn't look up the p-value here. I'll skip that because I'll kind of show you in a different way. And we went through, we said, you know, we're not going to reject at any level because the sample evidence supported the null. All right. So what I wanted to kind of get at here, maybe having a more interesting example. So I think this one is going to allow us to kind of hopefully connect the two, p-value and critical value approach. So here I want to test for whether or not the proportion of Indiana mothers that smoke is greater than 0.15. Okay. So what would my null alternative hypothesis be here? If I want to test for whether or not more than 15% of Indiana mothers smoke while pregnant,
Your alternative would be B is very when.
yeah, 0.15, right? Yeah. Then my null would be, well, I'm going to assume, sorry, the opposite is true, or that it's less than or equal to 0.15. Okay. So I take a sample of 400 mothers, and I see that 72 of them smoke while pregnant. So how would I find my sample proportion here? I know my sample size is 400. This is kind of an added step that's sometimes tricky with these proportion examples.
72 by 400.
Yeah, 72 over 400, or I believe that's a sample proportion of 0.18. Okay. So start out, I've got my null term. What type of tailed test do I have here? If I look at my alternative hypothesis, greater than, so greater than or a right-tailed test. So only evidence on the right-hand side of this assumed true value of 0.15 would go against the null. Well, I found something on that side, right? I don't know exactly where I can plot it here, but it's somewhere on the right, right? So I could use either approach here, the critical value or the p-value approach. So I'll first do the critical value approach since we were just doing that, and then I'll show you how the p-value approach would lead to the exact same rejection decisions. Okay? So if it's a right-tailed test, and I want the critical values that give me 0.1, 0.05, and 0.01 in these right tails, what are those values going to be? Well, we literally just looked those up, right? We had a right-tailed test here. It's going to be the exact same critical values. They're never going to change. When I go to that table and look up an alpha of 0.05, 0.01, and 0.1, I'm always going to find these same three values, right? And when you're looking at kind of like the practice exams and things, the options I give you, really once you look up one of these alphas, you'll be able to identify what all three are, right? Like, you know, if the very first one here for an alpha 0.01 is 2.33, well, then whatever option has 2.33 there as the critical value goes in alpha 0.01, that has to be the correct one, right? Usually those should be pretty easy, those critical value questions, because I'm just trying to test your knowledge about critical values for right-tailed test, right side of the distribution. Critical values for left-tailed test, left side. And then two-tailed test, we've got two critical values. So I think, you know, the way we write that is, you know, plus or minus whatever the value is. And then the only difference there is you have to look up not alpha, but alpha over 2, right? Alpha divided, just like we did for confidence intervals.
Is the test mostly multiple?
Yeah, so I'll do a kind of short answer at the end to kind of show, I'll be honest, to do hypothesis testing so that I can see if you were close, but just a little bit off in the calculation, or you're thinking about it right, but you did a left instead of a right tail test. I can give a little more partial credit there. Yep. So we've got this set up. I've got my 3 critical values now. The next step is what? What do I compare to my critical values?
Wait.
No, remember, so if we're doing the p-value approach, why are all my markers running up there? My p-value, I say, is that less than alpha? Yeah, if I'm using the critical value approach, I'm actually going to want to compare my test statistic to these critical values. So I have to turn my sample proportion into a test statistic. How do I do that? Well, I've got that formula. So it's just a matter of plugging in my values. Like this is a step I can't really, it's hard to give me a lot, or hard for me to give you a lot of help here because you have the formula in front of you. You've already identified your sample portion sample mean. And that P0 is just the assumed true value, so 0.15. It's a matter of plugging our values in here. Okay. So I get this test statistic or this Z statistic of 1.68. All I'm going to do is plot that. This is where I think drawing it out, if you really wanted to, you can remember that this is when you reject, right? So I reject if this is true. So is my test statistic greater than my critical value? I can compare it to every single one of these. I can make my rejection decision that way. If I draw this out and I plot that test statistic of 1.68 here, I can clearly see it's in the rejection region for an alpha of 0.1 and 0.05. So I would reject at the 10 and 5% significance level, but it's not in my rejection region for that alpha of 0.01. So I fail to reject at that 1% significance level. Okay. So here I reject the alpha, kind of think about the significance level 10, 5, and 1. Okay. Everybody on board up to this point? Any questions here? I'm then going to kind of show you how to connect this to the p-value approach in the last couple minutes. Except for I think I need to make sure. Gotta have a red marker that was in here somewhere. So let's say instead I want to do the p-value approach here. What I would actually want to find is that probability that I saw the sample evidence I did that was as inconsistent with what I assume to be true, or anything even more inconsistent. I've got a right-tailed test, so the area to the right. So what I need to do is turn that value into a test statistic, and then just find the area to the right of it. Okay. So I've got my Z value. My Z statistic is 1.68. So I go down to 1.68. So I can show this on, there we go. 1.68, 0.9535. Okay, my p-value is 0.9535. No. Well, why is that not my p-value? The table always tells me the area to the left. So for a left-tailed test, it's nice and easy because when I look at my test statistic, I automatically find my p-value. For a two-tailed test, it's not, or sorry, two-tailed. Right-tailed test, it's not as easy because the table is going to tell me the area to the left of my test statistic. I wanted the area to the right, so I had the added step of subtracting that area from 1. But once again, drawing that visual out, remembering that I'm always getting the area to the left from the table. Oh yeah, I've got to still subtract that from 1. So now I've got a p-value of what? 0.0465. Okay. So, trying to keep all this on the board here. We only reject if the p-value is less than alpha. So 0.0465, is that less than 0.1? Sure enough, I reject at the 10% level. Is it less than 0.05? Just barely, but sure enough, so I reject at the 5% level. Is it less than 0.01? No. So I fail to reject at that 1% significance level. So it doesn't matter which method I use, the rejection decision will always be the same. Right? So maybe on the short answer one, I leave that open to you, whether or not, if you like the p-value approach a little more than the critical value, you can use that one, or vice versa. Okay. Questions on this idea? Okay, so I'm going to do something a little bit different here. I think what I'm going to do so that you guys can study a little bit more for the exam. They say that you don't have to turn the Excel assignment in until after the exam, right? I don't want to waste too much time with the Excel leading into the exam. We've got one more kind of example we have to go through on Friday and then do a little bit of just kind of more hypothesis testing problems. So I'm going to hold off on Excel stuff until that Wednesday after the exam, right? So we'll kind of cover stuff on that Wednesday. Now, you should be kind of through the first 2/3 of that assignment, the confidence interval stuff we've already done. But that hypothesis testing part, I'm gonna save that and probably make it due the Monday after the exam. So we'll go over how we do this in Excel, which will kind of give us like a review after the exam of hypothesis testing, because we're gonna do some more, but just complicate it. And then you'll kind of have until that following Monday to complete that Excel sum. Okay? Does that sound fair?
Not the Monday we're taking.
Not the Monday we take the exam. We'll go over it the Wednesday after the exam. It'll be due that following Monday. So the 14th. So we're pushing it way off. But like I said, if you haven't done the confidence interval part, I might do that now so you don't forget it. I mean, that'll be kind of way down the road then. So we're just kind of holding up on that last portion of the Excel assignment. Okay. Any questions? All right, we got a little bit more material to go through on Friday. We'll do a little bit more, kind of go through hypothesis testing, preparing for that exam. Other than that, I'll see you guys on Friday.